Would you mind sharing the slides?
Yes, on it.
Thank you.
Now it should be visible.
They are. So welcome to the webinar of today on the topic of sustainable friction couple for electric vehicle application and performance evaluation, which is part of our WebLearn webinar series. And here you see some of the registrants for today. We are a somewhat smaller group today. Maybe it's due to we are hitting closer to Christmas and kind of other times that picks on our interest also. But you are most welcome, the ones that are here. Me talking is the one to the left, that is Stefan Brolin is my name, and later on you will meet my colleague Madeleine Zetterlind, I think, towards the end of the webinar. We are the ones hosting the webinar. But we are not that interesting. And the agenda for today is just this short introduction, and then we will continue with presentations with as the main focus and a discussion towards the end. And we will aim to wrap up in 1.5 hours from now. And the WebLearn project, which these webinars originated from, is a project where we built a platform for collaborative cutting-edge competence development for the metal and polymer industry. So we hosted during the pandemic times, we hosted 33 webinars with a worldwide audience. And it was so successful, so we decided to continue with these webinars, which attracts quite a lot of industrial professionals. So if you found your way here, you probably have read something about it. And just the orders kind of today, or the rules of today, if you are not the one speaking, please keep your microphones turned off so we don't get any sudden disruptions during the presentations. And if you have questions that are most welcome, do write them in the chat and we will address those in the end. And please take an active part in the panel discussion towards the end as well. And just so you know, the webinar is recorded and will be available to you afterwards if you maybe have a colleague that could be interested. And if you don't want to be seen on the camera, please have your camera turned off, but feel free to have it on, especially during the panel discussions, since those will not be recorded. And one of the last things, just to a reminder of Zoom, down to the left, you have the microphone on and off, and you also have the camera on and off. And a bit further to the right, you can open the chat box. If you want to write a question, you can address everyone, or you address me, Stefan, or my colleague Madeleine. Preferably not addressed directly to the presenters, as they will be occupied with presenting and might miss the chat pop-ups. And with that, I think I will hand over to our presenters of today. That is Samuel Aue from Automotive Components in Floby, and also a colleague here at JTH, Lucia Latanzi, that will present. And by that, I will hand over to Samuel. Thank you.
Thank you, Stefan, for that introduction. Yeah, just a moment. Yeah. Yes, you are all welcome to today's webinar. This will be the second webinar in the series. We had the first one in April this year. So more information about that will be provided later. Today we are talking about sustainable friction couple for electrified vehicle applications. And in the webinar today, we will talk, the focus will be on the performance test, real test evaluation, and result and the evaluation. So As I was announced earlier, my name is Samuel Awe from automotive company Fluby in Sweden. Yeah, the agenda will be a brief information about our company, automotive company Fluby, and a brief recap of the April 2023 webinar. And I will talk briefly on why a sustainable SICA desire for electrified vehicles, brake performance evaluation test, results, and evaluation, and finally, summary. Automotive company Fluby are located here in Fluby, about an hour drive from John Shopping. And this company was established in the 1950s. And since then, we have been producing or manufacturing different components, vehicle components, among which include brake discs, which are made from the traditional Greek cast iron material. And now we are developing lightweight brake discs from aluminum composite material, which we call SICA, which is the focus of today's discussion. We also produce a wheel hub, complete assembly of a wheel hub, as you can see from the truck. So complete assembly of wheel hub for truck. And we also produce connecting rod, different connecting rod of a different type and size. So this is then in addition, we are part of a Volvo car. So then a recap of the April webinar. So the following points were discussed. We discussed the purpose of a brake rotor in vehicles and factor influencing its braking application or performance. So these were discussed in April. Mostly all of us are familiar, those that are on vehicle. We know that brake disc is very, very important for safety, to stop, to decelerate the car for safety reason. So this is very, very important, and there are various factors that influencing that brake performance. So which we discussed earlier in April, and we also talk about essential properties of a brake disc material. What are the most important brake disc material? The mechanical property is very important, both at room and elevated temperature, and the ability to conduct heat away from the disc during braking application, and good wear resistance and corrosion resistance. So these are some of the properties that is of importance. Then we also talk about the challenges of adopting a new brake disc material. Traditionally, over decades, 100 years, Greek cast iron have been known for the material for making brake discs. But today, there are a lot of challenges also with this traditional brake disc because of its propensity for corrosion and low wear resistance and the rest. So new material is needed. And now that we're having electric vehicle, we also need to save weight. And also because the mechanical braking system for electric vehicles is less frequently used, so corrosion will be an issue. So this requires new material to be developed that can fit in the shoe and perform as well as the traditional material. So there are a lot of challenges are there in adopting new material, which we also discussed in the April. So, and we also talked briefly about standardized brake disc performance evaluation tests. We talked about the trend in the automotive industry, electric vehicle, and we also talk of circularity and the other. So I also give brief information about our journey of developing this lightweight aluminum rotor, over years. So it will be good if you could listen to that webinar, which will be, the link will be provided later on. For today, sustainable SICA disc. the benefit of this sticker disc to electric vehicle application. One, it has an excellent wear resistance, so which means low non-exhaust particulate matter emission, and there won't be any problem of meeting Euro 7 requirements. So with a sticker disc, and it has a good corrosion resistance, which means no brake failure due to corrosion will be experienced. It's lightweight, which about 30 to 70% upstrung mass can be saved. And what is upstrung mass is the vehicle mass that is not supported by suspension. So that is upstrung mass, which is, and by lowering this upstrung mass, which means driving range can be increased for electric vehicle, and also you can handling of the car will also be good. So we also have this material also have a negligible noise, vibration, and harshness. So there's no problem with NVH issue. So which means there will be good driving comfortability. It is durable, meaning that one aluminum rotor will be good till the end of life of the vehicle. So you don't need to change because it doesn't wear. So that will show in these results some of these points I've highlighted to confirm with real practical test to buttress that. I would also like to talk about some of the standard test procedure that is used anywhere in the world, either in Japan or in US or in Europe. So there is a series of standardized test procedure. I listed some of them so so that we could know. One is a Federal Motor Vehicle Safety Standard. It's a FMVSS 135. This is used to measure the speed, sensitivity, and performance stability of the friction couple. So that is a standard procedure used to establish the sensitivity of the friction couple in relation to speed, and stability in terms of coefficient of friction of the friction couple. Then we have another one, which is SAE J2522, which is also called AK Master Test. This test procedure is used to evaluate the cold temperature performance, wet effectiveness, and parking brake evaluation, ramp application. So, and another one we call the AMS 100 test to evaluate extreme brake duty on high performance cars by applying the brakes to create maximum acceleration without anti-lock braking system intervention. So, and the other one that I will also mention here is WATP, which is called the Worldwide Harmonized Light Vehicle Test Procedure. This is basically used to evaluate particulate matter or pollutant emission from the vehicle, either non-exhaust or exhaust emission. So this is these are standardized method of evaluating friction couple, and all these method I've mentioned here could be tested on a test rig, that is dyno test rig, or on a real vehicle, on-road vehicle driving. So they can be applied in any of those to evaluate that. Then performance, I will give a little detail about some of these driving scenario, the performance test. One is alpine descent. So what is alpine descent? We can also call it downhill test. Downhill test, as you can see from the picture here, the vehicle is moving on a downhill, and you constantly press the brake. So from 20 kilometers per hour downhill at a constant speed, you press the brake at that constant speed. So what happens is that you have a constant input of energy onto the friction couple, brake disc. So a lot of it is generated as you are pressing on the brake pedal. And this it's a long time, about 20 minutes of this test. As you are driving down, then you press the brake at that speed. So you are having a lot of heat energy generated. This must be passed, and this is to evaluate how how the material could handle this amount of heat generated during that instance. So it must be passed. And the next is fade test, which is also called AMS 100. This is to see how the friction couple could cope with under different testing conditions, extreme driving condition at a very short time, less than 2 minutes. So you have you drive from 100 km/h, then to 0. You brake at maximum speed to 0. So at 10 different occasions. So as you see, as you do this kind of series of tests, what happens? A lot of energy is built up. A lot of heat is built up in the, on the brake disc and the surface. So this could create a lot of issue. So there we can evaluate if there is a tarmac crack, because you apply brake and you continue. So there will be temperature gradient within the disc, which could lead to tarmac crack. You could also have fatigue crack. So all this is evaluated from the disc, and this also must be passed. Then another test is a single stop test. This one is driving at very high speed and you brake. This is used for emergency braking. So which is very short, less than 10 seconds. So you drive at a very high speed, and you brake to 0. So this, a lot of energy is generated within the disc, and you can see like a fire. So this, the disc must cope with this kind of scenario. And this must also be passed. The other one is a brake durability and wear test, which we need, since this is very important to understand the durability of the friction couple material, like corrosion cleanability and the NVH test, which is noise, vibration, and harshness. So because you don't want to be driving your vehicle and be hearing a lot of noise and series of sound, so it creates some kind of discomfort. So we need to evaluate that. And the other one is a PM emission. We all are aware of a Euro 7. So which means we don't want to generate a lot of suspended fine particles, so which can create a health issue to women. So these are some of the tests that are needed. Now back to the sticker itself, the material itself. Here you can see this is a sticker disc. It's a solid disc used for the test, and here is the microstructure. You have the aluminum alloy is reinforced with silicon carbide particles, as you can see in the structure. And before the test, the surface, the friction ring, is pre-treated. We have two techniques of doing that, either through chemical etching or we use laser texturing. And the essence of doing this is to improve the grain performance, or other words, to improve the bedding in, that is the transfer of at the beginning of braking application, to improve transfer of tribofilm on the surface. So that is done, and these were done together with the compatible copper-free NO pad developed by our partner, Federal Mogul. So these are the material, the friction couple we are talking about here today. And these tests were, as I've said earlier on, the performance evaluation can be done on dyno or through on-road vehicle test. And in this sense, we've performed both tests using dyno and as well as a vehicle on-road test. And for the vehicle, we use two different types of vehicle. We have Audi and Volvo car, as you see in the image. And the configuration of the vehicles are seen here in the table. And what are those tests? Like AK Master corrosion cleanability and PM emission were evaluated using dyno test. Then uphill descent was performed using the real vehicle on-road downhill test. Then AMS, LVH, and wear tests were performed both on the vehicle and the dyno. Here is the result from AK Master. From AK Master, we see here I show the first three test procedure and the fade test. So, and what we can see from here at the first, we see that quick creation of the building of a coefficient of friction. So we see it increase at the beginning, so quickly. So and we see at the coefficient of friction is almost around 4.2 or 3. So and we see in the bedding section, we see that this also is maintained and sustained even after bedding. So which is show that stability of the coefficient of friction. And for the fading, here fading is a extreme condition under 15 brake application. So and we see the green line is the pressure applied on the brake, and the red is the temperature. So at this 15 brake application, you see the temperature of the on the surface of the disc is increasing up to around 350, close to 350 degrees centigrade at the end of a 15 brake application. And we also see that as a result of that, the coefficient of friction a little bit decreased, but maintained throughout the rest of the. So which means a good resistance. And the next stage after fading, we see that recovery. You know, it recover quickly back to this close to 0.4 coefficient of friction. But this was not shown in this picture. But at the end, you see on the surface of the disc, you see it's darker, which shows the tribal film formation on the surface. And we see the part, so which is very, very good. That is what we desire for our brake friction couple. And here is the AMS and the uphill descent results. So from this AMS 100, here I show the last 5, because as I've said earlier on, there are 10 consecutive kind of braking events, but I choose to show the last 5 and the condition. You see the pressure applied, so I demonstrate the pressure almost around above 180 bar. So you see, and also we see the coefficient of friction here is stable, so almost at the same range in the last 5. That is from braking application 6 to 10. So you can see, so it's much stable, and which is very, very good. And the maximum temperature obtained is for the rear disc is around 319, which is good. And we also see that the transfer layer is very, very good as well. Then for the uphill descent, so similar experience were observed, and with a good the fluid temperature, brake fluid temperature at the end of the braking event, it was around 78, which is far, far lower to the boiling temperature of the brake fluid, which is around 180 degrees. So, which is good. And then we also evaluate the durability, LVH. So from this, we see that we investigate the propensity to produce noise. So, and the results indicated that good behavior at the end, as you can see from here. And based on this test result, we evaluated the lifespan of the pad and the disc. So, and take note that the vehicle that was used is a ICE vehicle, not electric vehicle. So, and we evaluated based on this result, we see that Sika disc left and right, no measurable wear. So, which confirmed the excellent wear resistance of the disc. But the pad, we evaluated the lifespan thereafter to be around the left part is around the 68,528 kilometer, while the right evaluated as the 68,243 kilometer lifespan of the part. And we also look at the corrosion cleanability of the disc. So from here, we compare the traditional GCI brake disc and the Sika disc. So we see here, you can see from here, after the corrosion, we see the rust and the pad. So, and we see the aluminum. And after the corrosion, we put the disc in the dyno. So to see how the part you can clean the surface of the disc at the end. And the conclusion from here is that looking into this, we see that there is a high stiction force. Look into the GCI and the pad. Inner board, you have a 972, and outer board, you have a 2,385 Newton. So which means high stiction force. So which means release force. It will create a lot of noise due to corrosion. So we see in a GCI, but in aluminum, it's 70 and 77, which is it's nothing. So which is a good point from that side point of view. In addition to that, we evaluated the DTV, that is disc thickness variation. So we evaluated it for the aluminum rotor, it's very negligible. So the DTV decreases from 13 micron to 8 micron. But for that of GCI, decreasing from 270 micron to 10 to 8 micron. So, and this will create the noise, Judah, what we call Judah. So it will create a lot of NVH issue due to this variation, because it will lead to vibration of the disc during the application. So due to that variation in the DTV. And we also evaluated the wear performance and the particle emission. So using different material concepts, the GCI and the hard-coated GCI and the Sika disc. So based on that, the results were plotted and using the WLTP procedure. And from here, we see that the particle generated from Sika is comparable to that of hard-coated GCI disc, so which is very, very low. And we also see that the PM10 is almost 78% lower compared to the GCI disc material, which means Euro 7 requirements will be easily met by this friction couple. And in conclusion, we see that from the brake performance evaluation, the friction couple show a stable coefficient of friction, fast creation of a stable tribal layer, and the corrosion cleanability test, we have a negligible disc thickness variation compared to GCI disc, no stiction, no corrosion issue, and also for the LVH durability test, which are good LVH behavior, long life durability of the friction couple. Also wear and PM emission test, excellent wear resistance and low brake pad wear, significantly lower non-exhaust PM emission. It was approximately 78% reduction of PM10 emission compared to that of the GCI. And the application of this friction couple will have a great benefit to the electric vehicle brake system application, by improving driving comfortability and weight reduction, which means by reducing the upstrung weight of the electric vehicle, it means it will improve drive range, it will improve acceleration of the vehicle, and since about 25% of e-vehicle weight is resulted from the battery, so this could also compensate by using this aluminum rotor. Then rust prevention and also environmental friendliness. And finally, this friction couple is a potential brake component for sustainable electric vehicle application. Thank you. Yes.
Thank you very much, Samuel, for the nice presentation. I think we will, do we have something in the chat already?
Yes, we have a question in the chat.
I will read the question. Samuel, aren't drum brakes better for electric cars with regenerative braking, except the high performance ones or trucks? They could be sealed and protected from elements owing to their sealed design. From Beamish.
Yeah.
So what do you say?
Do we answer the question now or when?
Yeah, you can do it now, and we can then move on. Yeah.
Okay. What was the question? Sorry. Sorry.
Okay. Aren't drum brakes better for electric cars with regenerative braking, except the high performance ones or trucks? Question mark. They could be sealed and protected from elements owing to their sealed design.
Yeah. Yeah. Depending on the design, yeah, the drum brake could be a good idea, but the brake disc or rotor, I think, is better due to the cooling behavior. So that would be the appropriate. And also, you see, if you talk of traditional disc, since the electric vehicle is not, the mechanical braking is not frequently used. So you might have an issue of corrosion if you use a drum brake with what is it called, with a traditional brake material. So that might be an issue. So if you use that, but and that, in addition to that, if you use a drum brake, then probably maybe it also may create some kind of weight issue. So with the traditional brake as well. So these are some of the, I mean, a lot of pro and cons. So you need to think about when choosing that kind of brake drum. Yeah.
Okay. Thank you. And maybe you can discuss further later on in this session. So thank you so much, Samuel. And we will hand over to Lucia.
Yes, thank you. I'm sharing the screen in the meantime. So I will continue on the same topic, but giving more university perspective on the aluminium-based composites. I am a postdoc researcher here at Jönköping University. I've been here for 3 years, and all my research activities have been in the field of aluminium-based composites reinforced with silicon carbide particles. And all the research activities have been in collaboration with AC Fluvi, actually. I will just, I will repeat some of the things that you already said, Samuel, but just to summarize the main advantages related to these aluminum composites. We saw together that aluminum composites in brake discs. So we saw together that one of the reasons is the upcoming electrification of vehicles, where the braking itself is changing dramatically. So we go from 100% of mechanical braking in internal combustion engine vehicles to only 10% of mechanical braking in electric vehicles. So it means that the braking efficiency is even more critical here, since it would be used in emergency situations, and we need to be sure to have a constant performance even after periods of inactivity for the brake disc itself. Another point was the sustainability requirements, since we know that standards and regulation are evolving towards new sustainability demands. And the last example is the Euro 7 that will deal with non-exhaust PM10 emissions with different limitation depending for the future years. And these MMC, so the metal matrix composites, are promising in this sense to help satisfying these new requirements that the standard gray cast iron cannot withstand. So again, briefly summarizing the advantages, we saw with Samuel that compared to gray cast iron, an aluminium-based composite gives you 50% lighter brake disc. The performance in terms of corrosion and wear resistance is much better. And also it comes in and to have 3 times greater thermal conductivity, because the thermophysical properties of the material is also are also critical properties when thinking of the brake disc application. But this is a good point for us in research, that there are still some challenges connected to this material. So we have something to do to further develop the material. For example, since it is aluminium based, we have some limitation related to the maximum operating temperature, and we hope to develop towards a higher maximum operating temperature for the composite. Being a composite, there are challenges related to the end of life evaluation and sustainability. So how can we recycle this material at the end of the life of the vehicle we saw? Because Samuel said, we saw together with Samuel that the brake disc will have a much longer lifespan than the gray cast iron equivalents, but then it means that the first product to end would be the vehicle itself. So how to treat it at the end of life and how to reuse this material and recycle it. And then also cutting and drilling, because of the presence of carbides, are still challenging and costly operations. So we have a lot to do still, and that's a good sign. And that's why it's critical for us in university to have automotive components. Fluby has a research partner, since they have the prototype production for brake disc with this material, and the name is Sikalite, as Samuel said. So the first research effort that we had together, it was this Pro4Al project that ended earlier this year. It was about properties and formability of aluminium metal matrix composites. It was in a collaborative effort between university and different industrial partners. We had Comptech, AC Fluby, Husqvarna, and Grenges, with different roles in the as actors in this consortium. And we had 2 different targets in the project. The first part was to do a matrix optimization for high temperature, aiming at improving the maximum operating temperature from 420, which is the current one, to 470, or in any case a bit higher, towards the 500 degrees. And then process optimization to reduce the cycle time, so to try to reduce also the cost related to the material. And then we wanted to do component validation for a clutch drum, for chainsaws, so from the Husqvarna side, and then the brake disc for Fluby. So looking at the first part of the project, when we went for matrix optimization, we started with our reference material, which is the Sikalite current solution. Is an aluminium 9 silicon matrix alloy reinforced with around 20% of silicon carbide particles. And then we looked into literature to support the selection of alloying elements and improve the mechanical performance of the material at elevated temperature. So we started with the nickel, which is a well-known element to be added to aluminum silicon alloys to form reinforcing faces, nickel-based, that are stable at high temperature. And also nickel is not on the critical raw material list of 2020 that the European Commission issued. Then we also looked into copper, because it is also known to interact with nickel in forming reinforcing precipitates during high temperature exposure. So the thinking was to have another mechanism of reinforcement that might be active throughout the life of the brake disc itself. Copper is also not on the critical raw material list, but it is a little bit more problematic in terms of environmental pollution because of its toxicity and also susceptibility to corrosion. We also looked into the possibility of adding lanthanum and cerium, so two rare earths, since they have been shown to have as-cast matrix strengthening in aluminum silicon alloys, but those are elements on the critical raw material list. So we explored that possibility to see if it was worth it taking in critical raw materials, but having a very clear advantage in terms of mechanical performance. So this was our preliminary study, but to move to component validation, as I showed you before, we decided given the results, we decided to stick with just nickel and then nickel and copper additions together. And that's what I will present to you today. So just to get familiar with the microstructure, what are we talking about in this case? So if we go to the scanning electron microscope, this is what we would see. The base material appears with a light gray matrix, and that is aluminum, the aluminum matrix. The dark polygonal features are the silicon carbide particles. So you see that they are quite polygonal and with sharp edges in the microstructure. You can clearly see them. The white parts here in the middle of the aluminum matrix is the eutectic silicon that comes from the matrix alloy. And these features will be also common to the other two materials. When adding nickel, we promote precipitation of nickel-based phases, and those appear white or very bright here in the center picture. So these here are the nickel-based phases. And you see that there is still eutectic silicon here in the background, but a little bit less, with less contrast, let's say, compared to the aluminum matrix. Adding a little bit of copper, it didn't lead to significant change in the microstructure compared to only nickel. We saw that copper was included in it was retained in the nickel-based phases and partially also in the aluminum matrix. So we didn't generate additional phases, but we strengthened the matrix and the nickel phases. We performed mechanical tests, as said, on all the materials. Now I'm presenting the results of compression testing at elevated temperature. So we went from room temperature and then we tested at 350, 420, which is the current maximum operating temperature, and then 470. And we saw clearly, first of all, also the effect of strain rate, but we can see clearly the effect of chemical composition in the matrix. So at room temperature, only the nickel addition led to an increase in the peak stress by 36%. This is the average at all strain rates. And further adding copper led to an additional increase of 9%. And this increase, as you can see, is maintained and even increased compared to the base material as temperature increases, so moving horizontally on the center line. While so this big contribution is due to nickel, because if we see above, then on the top line, the contribution is not maintained. So copper is not giving further support in withstanding the mechanical stresses at high temperature. in compression. So nickel is definitely a positive addition. Copper does not give a significant contribution in this case. We went to look into the microstructures to confirm of what was happening. So these are the samples that went under compression testing. On the top, you have the base metal matrix composite. So the sample was originally a cylinder that got crushed between the plates at high temperature. So this is the maximum temperature, 470. And you clearly see the flow of the material. So how the material got deformed under pressure, and it flowed away to the sides of the sample, and we had a little bit of extrusion here in the external side. But you see clearly how both the matrix and the carbides are moving, following the flow of the material. And here you see in high magnification that the dendrites of the matrix, and as a consequence also the eutectic silicon, gets stretched and heavily deformed to accommodate the pressure that is given during the compression test. If we look into the material reinforced with these nickel-based phases, you see already from on a macro scale down here that you cannot perceive the same kind of deformation that we had above. So the phases somehow, the nickel phases somehow are interlocking, and you see it here, interlocking with the silicon carbides and make the whole microstructure much more stiffer than before, and it can withstand the compression stresses more efficiently than the base material. So that resulted in that much higher peak stress, and we can see in the microstructure also what is happening. So there is a little bit of flow, but much hindered by the presence of such phases that are stable at high temperature. You see that they start to get not disintegrated, but reduced into smaller parts, but they're still there and they can interlock and hinder the material flow. So we checked the mechanical properties as said, and we also evaluated the elastic modulus to confirm this higher stiffness related to nickel-based phases. We also checked the thermophysical properties because, as said, that is also a critical point to look into for brake disc application. So we confirmed that even having these secondary phases, we have a slight decrease of thermal conductivity compared to our material. So from around 160 to 120, but still the value is more than double than what we have for gray cast iron. So we can, is a compromise that we can accept in this case, this decrease in thermal conductivity. And volumetric heat capacity instead is not affected in this case. So these results are quite promising, and we decided to move on from laboratory scale testing up to now to the component validation. So we produced full-scale brake discs with these two experimental materials, and we went for component testing with the AK master test and AMS 100 test that Samuel just presented, tested against the brake pads that were optimized for the Sika-Light material. So brake pads that are optimized for aluminium-based composites. You see here that the brake disc is ready to be tested. So for the AK master test, Samuel already explained it fully, but is a procedure that assesses the effectiveness behavior of a friction material for motor vehicles. And the purpose is to compare friction materials under equal conditions. So this is the all the sections that you get when running this kind of test. You have in every section you're testing with different parameters that you can change, and here you have the fading section that Samuel was showing before, where you have a temperature increase due to friction. This is just to visualize it a little bit easier than before. So as said, different sections, and on each one you determine the coefficient of friction of that section, and you also test fading with the temperature increase due to the friction itself developed at the couple. So if we look into the results with increasing temperature for our materials, we see directly a different behavior with increasing temperature. So the base material had somehow a constant coefficient of friction with then a sudden decrease above 300 Celsius degrees in temperature. The two experimental materials instead, they have a decrease that starts much earlier. We go to a valley here at around 250 degrees, but then the performance goes back up, and at the end we end with a slightly higher coefficient of friction for the material added with nickel and added with both nickel and copper. You see that the end point is slightly higher than what we had for the reference material. So this decrease here before another increase, we will have to further investigate that because we think it might be due to a different ribofilm that gets formed, probably in terms of chemical composition because of the presence of nickel, that somehow has a different behavior at this point, and then gets rebuilt or recovers the performance, goes back up, and then the decrease related to temperature at the end. If we look into fading, so we end up with the same result in terms of coefficient of friction. We have the decrease towards the end at the 15 brake application. The coefficient of friction is slightly higher with the two experimental materials, but most importantly, you see that the value of pressure that is required to obtain that coefficient of friction is much lower or with less variation compared to the reference material. You see here that the green curve is pressure. So here we have much variation in the pressure requirements to get a braking performance. With the two experimental materials instead, this width is very much reduced. So by the end of the test, at the same temperature, the coefficient of friction is slightly higher and less pressure required to get it. These were the lines for the comparison in terms of pressure and coefficient of friction. So if we look at the characteristic values in the fade sections 1 and 2, we have this has observed a slight increase with the experimental materials. And then also the report always provides you with the pictures of the pads and the disc at the end of the testing to then enable further inspection of the wear tracks around the disc and on the pad to investigate the ribofilm and to understand what happened during the test. If we briefly give a look also at the AMS 100 test, that was the fade test where we have 10 basic cycles, so 10 application of 10 times of the braking and following the temperature development due to friction. We can see that in this case also, as we saw before, the base material had a constant performance until the fourth application, and then a constant decrease of coefficient of friction related to the increase in temperature. In the case of the two experimental materials instead, we have, as observed before, we have this earlier decrease in the coefficient of friction, but then it builds up again. So the tribo layer has a different behavior, definitely, with the new materials. And then decrease towards 0.2 of friction at the end in all cases with the highest temperature. So here at the break number 50 is where there is the change of behavior. We reached the peak in the two experimental materials, while for the base material we were already in the descending area of the performance. So after to have a satisfying development of the material, it would be nice to be able to maintain the coefficient of friction above 0.27, also at elevated temperature. So to try to, the further development of the material requires us to, sorry, my PowerPoint just crashed, but requires us, okay, requires us to work on the, to develop the material focusing on the last, here, on the last part of the test to be able to get this curve above the yellow line to maintain satisfactory braking performance. Also with the AMS 100 test, you get documented of both the sides of the brake disc, so to further explore the wear tracks on the disc and the brake pads that were used coupled to that test. So just to summarize and have a small takeaway, in this project, we focused on increasing the maximum operating temperature of the aluminium-based composite. And these are the results that I showed you today. The takeaway is that moving from lab scale to component scale, the results are relevant because it's evident that we need to connect the mechanical performance at lab scale, the thermophysical properties of the material, and then the performance of the component itself. Since it is a complex situation with a number of variables, so it is useful to start small, but then it's also critical to end up with the component to be relevant to the industry, to give results that actually have a practical meaning. So for our future development, we will need to focus on this tribo layer investigation, understand the role of the chemical composition in the tribo layer, and also the role of temperature in probably disrupting it or being able to form it earlier. And then we can, once we have this knowledge, we can target better the parameters that will allow us to increase that coefficient of friction, to maintain the coefficient of friction above 0.27, let's say, even at the high temperature, so at the end of the AMS 100 test. With this, I conclude, and I thank you very much for listening.